Hello, this is Dr. Muhammad, and this is another video under the Seismic Design of Structure class. And still we are talking about the detailed seismic provisions of ASCE-7. And today we're going to talk about the P-delta effects, and it is going to be part 1. There is another video I'm going to prepare for part 2. For this part, I'm going to talk about the P-delta concept, and I'm going to explain about the geometric stiffness and the stability coefficient, and we are going to talk about some important hints regarding them and how we can understand them in our seismic analysis and design. Okay, now let's go directly to the main concept of P-delta effect and understand more about it. Okay, so now let's go to the an important graph that is always used for explaining the effect of P-delta. If we're going to have the pushover curve of any simple structure, and this pushover curve usually it is we can relate the displacement of the roof, for example, with the base shear force, which is V, and on this graph we can plot the curve of the structure. So we are plotting here a very simple structure. This is a simple structure, as you can see it here, and we are having like two pushover curves here. One is the dark one, and the other one is lighter one, as you can see. And we are claiming that the dark one, which is, as you can see here, this is the pushover curve of a structure excluding P-delta. Okay, this is with the exclusion of P-delta. And the other one, which is this gray, it is including P-delta. So this is what we have observed when we draw the pushover curves of the same building with and without P-delta effect. So from here we can build our main concept of the P-delta and start to think about it in a different way. First of all, P-delta, commonly whenever we have a structure and this structure is loaded vertically, we are concerned whenever that it is loaded with a load, vertical load, which is gravity loads coming from the different stories. And under the earthquake there is a shaking, and this shaking would make our structure to lean aside like this. We are afraid that this vertical load that is applied, okay, P, is going to make additional moment and straining actions on the members that is going to resist this P-delta, which is the main resisting system. So from here we are talking about this concept, which is the P-delta, or the effect of the gravity load when the structure is going to move laterally due to earthquake. So from here we are going to think about the structure in a different way. We want to know what is the effect of the P-delta in general, how it would affect the structure. This graph actually would give us a great deal of understanding for the P-delta. First of all, this initial stiffness, as you know that in the beginning of this series I have spent time on the initial stiffness and the different type of stiffnesses of structures. So the first line, or the first part of this pushover curve, of the dark pushover curve, we call it initial stiffness. And as you can see, we have a specific point here which is distinguishing between the linear part, which we call it the linear elastic part, and the other flat part here, which is the plastic part. This point is going to be given a name, or designated on the force axis, which is the base shear axis. We call it V node Y, which means that the initial, or we can say it is the original building base shear at yield, the level of force that is going to distinguish between the elastic and inelastic part of the structure. And the corresponding displacement, we are going to denote it as delta yield, or delta node yield. So you can put it like this: delta yield, it is okay, or delta node yield. Both are okay, and I'm going to explain why we put them like this. But anyway, this is the delta yield, which is relating the displacement or the point that is corresponding to the base yield base shear. We found when we are considering P delta, this means that after having the translation or the delta of the structure under the load, we found that the behavior of the total structure or the whole structure is different, as you can see in the gray graph here. So we found that the structure is behaving like this. First of all, the initial slope, which was denoted as K node of the building without P delta, we found that this initial slope is having more, or this slope of the original building is going to be changed if you compare it with the other gray graph. So we have K node, which is the initial slope of the structure without P delta. We have K1, which is the slope of the structure with the inclusion of P delta, and it equals to K node plus Kg. Now we understand what is the meaning of K node, the initial stiffness slope, but what is Kg? This is what we want to understand, and this is what we are going to explain in the next slide. Okay, so now we have this graph, and we can tell from this graph that inclusion or including P delta in the analysis of the structure and the design of it would affect two things. First, the stiffness would be changed, and second, we will find that there is a point here which is considered to be the maximum strength of the structure. We will find that it is different than V node yield. It is going to be given a title or a designation called V1 yield, which is the maximum capacity of the structure with the inclusion of P delta. Okay, and the corresponding displacement for this V1 yield, we found it surprisingly, it is the same delta yield also here. So this is why we put it as delta yield or delta node yield, which is the original structure without inclusion of P delta, or delta 1 yield. All of them, they are the same. And this is something that, like phenomenon, we found it like this. This point is the same. I mean, in terms of displacement. Okay? So the displacement, or the point of displacement that distinguishes between the linear and nonlinear behavior of the structure, it is going to be the same, or it is the same before and after inclusion of P delta. And based on this, we can claim that the P delta effect would affect the stiffness of the system and the strength of the system. The stiffness, which means the slope is going to be changed, as we have seen here from K node, it will be K1, and the strength is going to be changed from V node yield to V1 yield. And this is what we put it here in this note. P delta effects influence both the stiffness and strength of the structure. So that's important conclusion that we want to keep in our mind. Stiffness and strength is going to be changed. However, the yield displacement is not going to be changed. This is something that we want to highlight, and this is what I put it here. Inherent capacity of the structure is the same in either condition. The yield displacement is the same. The inherent capacity, I mean that the yield displacement here, okay? The capacity in terms of the yield displacement. Okay, so this is an important issue we want to understand when we look to the structure. Let me remove everything here to make it clearer. So first, stiffness and strength is going to be changed due to the inclusion of P-delta, and in the same time the yield displacement would remain the same. The yield displacement would remain the same. Okay, this is what we can understand from the inclusion of the P-delta on the system pushover curve. Okay, now let's go to understand about KG, or what we call it the geometric stiffness. What is the meaning of geometric stiffness? Actually, if you have a building something like this and you have P, which is the gravity load, take care, we're talking about the gravity load here, okay? And the height of this floor, or the height of this building, if we are talking about one-story building, for example, is H. So we are going to provide or introduce a parameter called geometric stiffness of the structure, which is going to be designated with Kg, is equal to P over H. So P over H equals to Kg. This P, it is the gravity loading, and this H is the height of the system, where P is the total gravity. Take care, we're talking about gravity here. Gravity means that include everything, maybe dead load, live load, snow load. Okay, it's not the seismic weight. Take care. And H is the story height. So we put it like this: Kg equal to P over H. Okay, Kg is negative where the gravity loads cause compression in the story, and this is common. If this P is negative compression, then this stiffness is going to be negative. And the opposite, if it's positive, it is going to be positive. But what is important for us when we look here, you're going to find that the difference between the two slopes we have here, this is the slope of the system. Okay, here, this is the slope of the system without inclusion of the gravity, without the inclusion of P delta, and here this is the slope where that we are going to include it, right? So we have, this is the angle here and here. This one is K node, this one is KG. Sorry, it's not KG, it is K1, which equals to K node plus KG. So as we denoted it before here, this is K node equal to, sorry, this is K1, which is equal to K node plus KG. So KG, it is what? It is the geometric stiffness, okay, which is P over H. So this difference, the slight difference in the slope, the slight difference between the two, it is giving us the geometric stiffness, okay? So this slight difference, it is based on P over H of the system or the structure, okay? Okay, now let's go to the next part also, which is important definition for us, calling stability coefficient theta. The stability coefficient theta. The stability coefficient theta is defined as the absolute value of the geometric stiffness divided by the elastic stiffness. So we are going to talk about this stability coefficient. We call it stability coefficient theta, which is equal to Kg over K node. Kg over K node, the absolute value of Kg. Remember that we said that Kg equal to P over H, which is this one, P over H here, and K node, it equals to V node yield over delta node yield, right? We have, this is delta node yield and this is V node yield. So substituting here, it's in the denominator. So we have V node yield here and delta node yield here. And this is the coefficient or the stability coefficient. Okay, this is the stability coefficient here. Okay, now this is why we are talking about this stability coefficient and why we have taken it as an indicator for the P delta. The point is we want to know if I'm going to tell you that we have two structures, maybe in the next slide I'm going to explain it more, but I want only to let you know or have some intuition regarding this. If we have two structures, both of them, they have the same gravity loading, which is P, but they are having different H. What will happen here? This system, which is shorter, it is going to have less if we are saying this is PH1, this is H2, so if we say that P over H1, it is going to be KG1, and we are going to have KG2, it is going to be very small here, P over H2. Okay, so H1, it is smaller than H2. This means that KG2 is going to be what? Smaller. This means that this system is like susceptible to P delta. Why? Because this KG, when we have H2 to be very large, high, the structure is going to be really susceptible. You can even feel it. If you have a very tall structure and you have like the gravity loading, this structure, like, it is similar to, like, as if we're talking about slenderness, for example. So the structure is going to be a little bit not stable if there is some heavy loading on it, right? But if it's short and compact like this, we're going to find that the stability or the geometric stiffness is going to be larger, right? Kg is going to be larger, right? So from this concept, or from this idea, we are like having a relation between the geometric stiffness and the elastic stiffness. Take care. This elastic stiffness, it is lateral stiffness. However, Kg, it is what? It is vertical. If you want, you can say that it's vertical one. Vertical, okay? Vertical, if you want to say vertical stiffness in the, okay, means that it is something related to, as we said, it is related to P over H, the gravity ratio to the height. However, K node, it is totally different. It's the lateral base shear over the lateral displacement. Totally different, okay? So this coefficient is like measuring the ratio between the geometric stiffness and the elastic stiffness, or between the vertical stiffness and the elastic stiffness. It is not very right to say vertical, because maybe some people would say that it is the like axial stiffness, but actually no, it is totally different. Here we took it, or we call it geometric stiffness, in order to say that it equals to a ratio, only a ratio between P over H, gravity loads over the height of the story or the structure. Okay, now we have understood what is the meaning of the geometric stiffness and the stability coefficient. Now let's go to another point, which is, now we want to know what should we do and how we can evaluate this stability coefficients in terms of the main two engineering demand parameters that we use, which is the base shear and the displacement. We want to know what is the effect of this coefficient on the structure capacity and on the structure displacement, or in the story displacement. So we are, as we have said here, if you look to V1 of the structure, you're going to find that it has been reduced. So it was V node and then reduced to V1 yield. How much reduction happened here? We can claim from the geometry, we can claim that V1 yield equal to, or we can say that V1, this height over this height, so V1 yield over V node yield, this over this, equals to, without thinking too much, we can think about that is the difference in the slopes, right? It is going to be like 1 minus theta over 1, right? Because the difference in the slope is going to be or theta, which is, this is the, actually theta is the ratio between the difference of the slope, kg, over k node, right? Remember that here, the slope, the initial slope is k node. The slope with the inclusion of p delta, it is what? K node plus kg. So it seems that as if this theta is measuring for us the difference between the two over the original initial stiffness. That's it. So this theta is giving us this concept that how much this difference in the slope, okay? What is the ratio of this difference? Kg, which is, we can say it is like this, like K1 minus K node over K node, right? This actually K1 minus K node over K node. This equals to theta, as we have explained here. This K1 minus K node, it gives us Kg, okay? So that's the point here. And based on this, we can say that V1 yield is going to be, this is 1 actually, so V1 yield equals to V node yield times 1 minus theta, V1, V node yield times 1 minus theta. And that for an applied force, this is actually for the yield, we're talking about the yield, but what if that we are designing at any point here for example, or here. So this is going to be V, only V, right? So for an applied force V, which is less than or equal to V1 yield, we are going to think about the corresponding displacement now. What is the effect on the corresponding displacement? Look here, this is delta node, and this one is going to be delta 1, right? If we're talking about the structure that is at the same V, for example, here, for any V, here at this level, this is we're talking about this V here. So we're going to find that they are different. There is a difference. This is delta node, and there is delta 1, right? What is the what is the ratio between the two? Also, it is going to be related to 1 over theta. It is the horizontal. If we're going to talk about the triangles similarities here, we're going to find that simply delta 1, as you can see, it is larger than delta node. So it equals to delta node over 1 minus theta. So now we can understand something that is very important, that the capacity of the structure, which is V1 yield, is going to be reduced by this value, which is 1 over 1 minus theta. However, that the displacement corresponding to any base shear at any level equal to the yield or less than it, the displacement is going to be equal to delta node over 1 minus theta. Okay, so now this is an important outcome for us. Look here to the theta. Look to the theta here. If it approaches 1, what will happen for this? When this theta approaches 1, the denominator is going to reach 0, and in this case, delta 1 is going to be, yes, infinity. This means what? Static instability. This would bring us to static instability. Okay? So as theta approaches 1, delta 1 approaches infinity, and V1 approaches 0. That's right. Defining a state of static instability. Defines a state of static instability. Okay. So now this is the case for us. Let's go to another slide and see what we are going to say. So now after having this like introduction, we are going to talk about the code provisions regarding P delta. Code provisions regarding P delta. Okay, so now this is the we are going to talk about the code provisions regarding P delta. Now let's go. From ASCE-7 item or section 12.8.7, you're going to find the definition here. I'm going to read it because it's important, and I'm going to give some hints about it. So P delta effects on story shears and moments the resulting member forces and moments, and the story drifts. So we are going to talk about three things here, which is member forces and moments. Forces, moments, I mean that like straining actions on the members, and the story drifts, which is related to the story, induced by these effects, are not required to be considered where the stability coefficient theta, as determined by the following equation, is equal to or less than 0.1. What is the code is talking about here is that he is telling that there is an equation that we're going to explain now, which is similar to what we have explained before. If the effect of the P delta is going to be small, and we are going to put a threshold here, which is 0.1, for example, if it's small, then we are not going to include P delta. P delta here is not going to be included. We are not going to calculate anything for it, and we are not going to increase or augment the member forces and moments and drifts of the stories. This is what the code is trying to tell us. So first of all, he is putting like a minimum here. He is putting a minimum. This minimum, as I said, the intent of this minimum, he is telling that this theta, which is the stability coefficient, as I'm going to explain it now, if the theta is small, if the ratio between kg over k node is less than 0.1, then we should not take care, we should not like include this P delta. Its inclusion should not be calculated and taken into consideration. The minimum actually here does not mean that P delta is not existent. Actually, it will be existent. If it's like, for example, like 8% or 0.09, for example, P delta is there. But the point is we are not going to calculate for it. We are not going to increase the forces, for example, and moments in this case. What is the reason for this? Why we put this minimum? Actually, we are putting the minimum here for the case that the structure over strength is going to take care of any existent P delta in the system, okay, when theta is less than 0.1. So it doesn't mean, as I said, that P delta does not exist or not important. Actually, it is going to be there, but the system over strength is going to take care of it, okay? But if the theta is larger than 0.1, in this case, we are going to find that we need to increase the forces and moments and drifts of the system, okay? So it's not enough for the overstrength of the system to take care of the P delta. We need to take care of it by ourselves, okay? So now this is the main reason for this minimum. Let's go to the theta that is given by the code and explain how it is actually similar to what we have explained before. Theta equals to px, so it is px times, this is the gravity loading, and I'm going to explain the definitions in detail here in a while. So px times delta, it's the design story drift, IE over CD. Actually, these IE and CD, we didn't include them before here, right? But actually, this delta node yield, it equals to, this one equals to delta, the design story drift, times IE over CD, right? This is the elastic. We're talking about the elastic displacement here. We're not talking about the design story drift or the design drift. We're talking about the elastic one, okay? Before being increased to obtain the delta, okay? So that's only the main difference, and the remaining is the same. So we have P delta, so we have P times delta here over V times H, V times H, it's the same. Vx here, it is the seismic shear force acting between the levels. I'm going to talk about this between the levels X and X1. HSX, it is the story height below level X, okay? And of course IE and CD, we know them very well. It is IE, it is the importance factor. CD, it is the deflection, it is the deflection amplification factor that we can obtain from table 12.2.1 or -1. Okay. Okay. Now, let's go and understand more about this. Let me clear this here. Okay. First of all, the intent of this section, okay, the intent of this section is to determine whether P-delta effects are significant or not. So we want to know if they are significant, then we are going to take into consideration the analyses. However, if it's not significant in this case, and if so, we are going to modify the strength and the stiffness of the structure to account for such effects. Let's go back here. Do you remember this curve? Now this is the structure inclusion with the inclusion of P-delta. But if we know that the slope is going to be large, or the difference in the slope is going to be large, Kg is high, this means that we need to increase this V yield. We want to increase it. So we are going to multiply the forces or the design forces of the members in a factor that is higher than 1. Also, the displacements need to be, or the story drift needs to be, need to be augmented, right? So that's the main reason actually for this. So this equation is a limit for us. We are going to get the value or obtain the value of the stability coefficient to compare it with the minimum. If it's less, then the P-delta effects are not significant, but they are existent, and overstrength will take care of it. But if it's higher than or larger than 0.1, then in this case the strength and the stiffness of the structure need to be, yes, we need to increase we need to adjust the strength and stiffness of the structure to account for such effects. Okay, let's now read the definition one by one, and I'm going to talk about these comments here. Px, it is the total vertical design load. Take care, vertical, as we were talking about vertical loads here, huh? It's not lateral loads. And design loads, okay, and these design loads, they are like, we said vertical means that like gravity loads, like dead load, live load, and snow load. At and above level X, if we're talking about one level, so we are talking about, if we're talking about multi-levels, for example, here. So if we're talking about this, so, or this level, so the gravity at this level here, which is at this story and whatever above it, okay? Where computing Px, no individual load factor need exceed 1. It does not, here it means that we are not using factored load. We are using service load, okay? Because it's like the check for the drift or the serviceability. No need for the augmentation, no need for increasing or using load factors. We are not designing here. It's totally different. In the design, yes, we are going to increase the loads by factoring it by values higher than 1. But here, no individual load factor need to exceed 1. We are going to use dead load with live load and snow load, the actual loads, okay? And this delta, which is design story drift, take care, we are talking about the design story drift as defined in section 12.8.6. We have explained this in previous video, please revisit that. Occurring simultaneously with Vx, and that's right, this is the design drift, which is going to be corresponding to Vx. Corresponding to the Vx. What is Vx? It is the seismic shear force acting between level X and X minus 1. Okay? It is the base shear that we are having here. This is the base shear. We have a base shear here and we have a base shear here. So the difference between the two. Okay? Seismic shear force acting between level X and X minus 1. Why we're talking about between level X and X? Because we are talking about individual story. We are checking for the individual story. So we have like, so we have like one story, another story. We are talking about the P delta for this story only, for example. So we need to know how much, what are the forces? So if we have a force here like this and we have another force here, so the difference between the two is going to make the P delta on the system. So this is why we are dealing with x and x minus 1 at these two levels. HSX, story height below level x. If this is x, this is x minus 1. So the story height, we're talking about the story height below the level x. Okay, the story height below level level x. Okay, now, and CD is going to be the deflection amplification factor. Story height, sorry, this is HS, which is story height below level x, and CD, it is the deflection amplification factor. Okay, now let's go to the next, and this is CD as we said from section 12.2-1. Okay, another thing that is no factor loads, as we said, it is no factor loads, it is only service loads. And here I mentioned about that if we have less, if theta is less than 0.1, means that the structure overstrength will take care of it, or I mean that it means the P-delta, instead of making calculation by us. So that's the important of understanding why we put a minimum. So if I ask you what is the reason for putting a minimum, the answer is for the answer for this, why the threshold or the minimum threshold there, because overstrength is going to take care of the P-delta. Okay, that's the answer for this. Okay, now let's go to the remaining part of this section in ASCE. The stability coefficient theta shall not exceed theta maximum. So now we are putting another threshold which is related to the maximum. So theta maximum should not be exceeded, determined as follows. And this theta maximum is going to be included with 0.5 over beta CD, and it should be less than 0.25. That's the maximum theta that we should consider. Okay? What is, we know theta, we know CD, but we do not know what is beta here. This beta is the ratio of the shear demand to shear capacity for the story between levels x and x minus 1. This ratio is permitted to be conservatively taken as 1. So this means that how much strength that the story is provided or providing and how much demand is existent. That's the difference between the two. Commonly this beta, actually the capacity of the system or the story, it is larger than the demand. Commonly if we designed it, if we designed the structure. But if we want to be conservative, we're going to say that beta equal to 1. This means that the capacity and the demand are equal. So actually when beta is going to be 1, this is the only value, the maximum value here, then theta maximum is going to be calculated based on this one. If this beta is 0.8, for example, this means that the theta maximum is going to be increased, the threshold is going to be increased, and this is not conservative, right? So we need to put the minimum limit for theta maximum available for us. So this can be obtained by putting beta equal to 1. Okay, I'm going to talk about this in the examples in the next video in general. Okay, now if I ask you a question, which is why we put theta maximum, why there is a maximum threshold, as I asked in the previously, why we put theta minimum, and we said that because overstrength is going to take care of the P-delta, no need to calculate, and the P-delta is not significant. And here if theta maximum is put, so is being put as a threshold, why we put it? The point is we want to like limit something called residual drift. Residual drift. So let me put it like this. The intent of this requirement is to protect structures from possibility of stability failures. So that's the main reason here, stability failures triggered by post-earthquake residual deformation. What is the meaning of residual deformation? Whenever that we have structure similar to this one, for example, and there is some earthquake is striking it, after the striking of the earthquake and looking to one point, which is this point, for example, here, we found that the structure at this point is making the interstory drift, as you can see here, and then all of a sudden there there is a kind of a failure or a local mechanism here happens, and then the structure is making another kind of wave signal, as you can see here, but it is away from the zero. Here we started from zero. This means that the structure, if we have the drift is making something like this, this means that the drift or the structure is going back and forth, left and right, to the stability or neutral position. But if it goes after that, goes like here and make this kind of waves here, this means that the structure already leaned. There are some residual drift here. We call this from the zero, here this is zero, until this axis for this waves here, we call this as residual drift. So, well, what will this residual drift do for us? It is similar to this here. You'll find the structure after the end of the earthquake, it is like this, leaning structure, something like this. This leaning phenomenon or this residual drift, it is the main reason for stability failures, especially post-earthquakes, after earthquakes. So we're not talking about the inside or during the earthquake, we're talking about after earthquake. This residual drift is going to be the main reason for stability failures. And then the decision of demolition is going to be taken based on this. Look to this, for example. This what happened in one building, as you can see here. This is in Tohoku earthquake in Japan, I think 2011. And this is San Fernando earthquake in United States in 70s, I guess. So here the residual deformations control demolition actions. This structure, what happened now? It is the earthquake already gone. What happened here? You can see that the columns are leaning. This means what? The entire story is having this P-delta. Okay? Okay, and this would make problem for us. This structure will not work for us. So it needs to be demolished. Similar here, look to this. This is the column here, and this is the column here, leaning column, and this is the vertical one here, okay, and vertical one. So it seems that there is an extreme residual drift happened due to the P-delta also. So now we cannot renovate, we cannot like retrofit the structure, we need to demolish it. Okay, so now we can understand why we put the maximum, theta maximum. It is directly related to the potential of residual drift that is going to be existent after earthquakes, and this would trigger what we call it the stability failures. Stability failures. Okay, now let's go to the next slide, and I hope that after that we are having a good idea in general about the P-delta. So now let's talk about this stability coefficient. This equation is used to determine the stability coefficient of each story. Take care of this word. We are talking about each story, not the entire building. Okay? Where the stability coefficients exceed 0.1, P-delta effects must be considered using one of two approaches. Yes, we have to consider two approaches. One of them need to be used. And this is actually written in the code here. Approach number one. So I mean now if we have already this P-delta, it is larger than 0.1. So what should we do in this case? We have two approaches. The first approach is the displacements and member forces are going to be multiplied by 1 over 1 minus theta. This is larger than 1. Okay? 1 over 1 minus theta to reflect the conditions shown in this figure. Okay? Because we want what? We want to increase the stiffness and the strength. So member forces, it means that the design member forces is going to be increased so that the strength is going to be increased in this case. We are going to lift it up. Similar for the displacement. We are going to increase the design displacement by this value. Okay, so we are going to multiply the member forces and displacements by 1 over 1 minus theta to reflect the conditions shown in this figure. Okay, in accordance to the equal displacement rule. Actually, this is an important issue. For equal displacement rule, as I mentioned before, two or three videos before, if we have the initial unlimited elastic behavior of the structure, and this is the demand spectrum, then you are going to have delta to be here, right? If it is going to be, the stiffness is going to be changed like this, and the unlimited behavior is going to give us corresponding displacement like this. This difference is the difference between the two structures, and it is based on the difference in the initial stiffnesses. So based on this, if we increase our stiffness from here to here, this means that the delta is going to be decreased. Delta here means it is the equal displacement rule, because the structure here is going to move like this. I mean that the pushover curve, the actual structure is going to make like this. And we said that equal displacement rule means that the displacement that is going to take place if there is unlimited elastic response of the structure equals to the actual or the inelastic displacement of the structure. Okay. Anyway, this is the first approach, which is multiplying the displacement and the forces by this factor, and this factor should be larger than 1. Okay, this is common. The second approach, which is using rational analysis, displacements and members and member forces are determined by rational analysis. This is the only case for us. Rational analysis, what is the meaning of rational analysis? We're going to see here. Rational analysis means that two types of rational analysis are envisioned here. We have the first one is the nonlinear static pushover, and the second is the nonlinear dynamic response history analysis, two of them. So what we are going to do here for the pushover curve or for pushover analysis, what we are going to do is, when we are designing the structure and assuming the member cross sections, we will check what is the pushover curve will be after the yield point. If there is positive post-yield stiffness, this means that there is no effect for the P-delta. It is okay for us. But if there is something similar to this, this means that P-delta is going to be there, and we need to take care of it, and we need to redesign our members. And this is what I put it here. A nonlinear static pushover analysis could be performed to show that the post-yield slope, this is the post-yield slope here. This is the yield, this point here, and this is the post-yield slope of the pushover curve is continuously positive. This is positive here, okay? Because we have three different levels of the post-yield stiffness, like strain hardening, elastic, perfectly plastic, or softening. So if the pushover curve is experiencing strain hardening, then no problem with this. Our system is okay. Okay. But if there is softening, something like this, there is a problem. P delta is controlling, and we need to increase the member sections and so on and redesign it. The second is going to be another kind of analysis, which is nonlinear dynamic response history analysis. Could be repeated. We're going to repeat it with and without P delta effects to determine if the behavior including P delta meets all performance criteria. So this is another issue. And instead of pushover curve, we are going to use nonlinear time history analysis, and we are going to see, for example, in nonlinear time history analysis, we are going to look if there is a kind of behavior for one drift or one story drift ratio that is making residual drift. This means that it is not acceptable. If we're going to check for the members and we found that the structure with P delta is having more straining actions compared to the case without P delta, then we need to look to the criteria. I mean that we need to check the criteria. We need to check the displacement, and we need to check the forces. Okay, so here nonlinear dynamic analysis is like total solution for us. If you use it, it's more accurate, and you are going to compare the results before and after P delta. If P delta is going to make some significant changes, then you need to take it into consideration and redesign your structure. Okay. Actually, this part, it is related to the dynamic instability for using nonlinear time history analysis. This curve, which I was explaining before, if you remember, we were talking about the elastic part, right? I didn't mention about the inelastic part at all. So here we are talking about this. This is actually from FEMA 750P, 750, talking about this point, but it is important to be highlighted. The real issue is dynamic stability. We found that the most accurate one is going to be nonlinear response history analysis. Okay, I'm going to talk about this in the future videos. We found that it's the most accurate. This is why it's very appealing for us. But this analysis also, it is very sensitive to many things. It is very sensitive to the ground motion, the initial stiffness, and the strain hardening, hysteretic behavior, the magnitude of the gravity loading. So it is highly sensitive. Okay, so this means that unfortunately the dynamic responsive structure is highly sensitive, as I said, to such parameters, causing considerable dispersion to appear in the results. This means that you can run two analyses with different time history records, and they are going to give you totally different forces and drifts. So what should you do here? So there is a dispersion that is going to be there in the results. The dispersion, which increases dramatically with the stability coefficient theta, is due primarily to the incrementally increasing residual deformation. Yes, this is the point that I want to highlight. It seems that residual drift is going to be your main criteria for judging whether or not this structure is going to have significant residual drift or not. And based on this, you can judge the structure is okay or not okay for nonlinear time history analysis. Okay. Remember, Will, all the equations that I have explained before, it is something approximate, and it is in the elastic range. What will happen in your structure is based on this, based on the nonlinear dynamic analysis. This is the reality. This is what will happen, really. Residual deformation may be controlled by increasing either initial strength or secondary stiffness, and this is actually can be given in detail in this paper. It's a very important paper, okay, by Gupta and Crunkler, and I think that it gives very details about the issue of the stability, dynamic stability for structures, and the inclusion of or understanding more about residual deformations. This is a script or part of it. You can find it in this paper. You can find it on the internet. And this is actually, they were giving some two curves for 20-story building in Los Angeles with and without P-delta. This is without P-delta, and this, this is no P-delta, and this is with P-delta. So this one, it is no P-delta, so there is what, as you can see, it is as if the positive kind of post-yield stiffness, but with P-delta, there is some plateau here for constant strength, and then going down, stiffness, softening, this is softening, negative stiffness or negative slope. This is a problem, and we need to consider it. And in their paper, they applied also nonlinear time history analysis for using some different SAC under the SAC project, and they were discussing about the residual drift and so on. It's a very interesting paper. I strongly recommend it for you to know more about this issue. Okay, the last thing that I want to highlight here is the reason for using the initial elastic stiffness in P-delta check, that we didn't mention anything about the post-yield or the nonlinear range or inelastic range. And this is actually kind of from Taranath book, if you are familiar with Taranath book, Tool Building for Design Steel, Concrete and Composite System. Actually, he was talking about why the code is not using anything related to the inelastic part. And I think that the first justification for him, it is reasonable actually. But in the second one, I think that I have some comments on the second one. So I'm going to share with you only the first part. he is talking about that many structures display strengths well above the strengths implied by code level forces. This overstrength likely protects structures from stability related failures, and that's the point here that I have explained before, that overstrength of the structure is going to take care of the P delta, and it is like enough for us to use elastic range to judge the P delta for the structure, because we are having a spare strength in our hands, which is the overstrength. Okay, I think that this is the end of this class, and I think that I'm going to stop it here, and in the next video I'm going to talk about some examples and implementation of P delta and real example. Okay, thank you and see you in the next video.